Daar houdt het van. Perfect. Ziet er goed uit. Ziet er goed uit, hè? Jo, loopt een beetje achter. Waarom dat zo heet, weet ik ook niet. Goed, stop, goed. Oh, dat is niet goed. 100. Clock. Okay, students, welcome to the fifth and last lecture on Matlab in engineering mechanics. We only have 5 lectures. Why do we only have 5 lectures? Well, the thing is, of course, that there are 2 ECTS for this course, and I think I can cover enough ground with these 5 lectures and the 5 homework assignments. So for today, homework assignment number 5 is open. Please hand it in over a week, and then you can finish the course by making the final project. And please look at the dates on Brightspace about when that will be released and when it will have to be handed in and reviewed. I'm not going to repeat the details here because I'll probably make an error, and all the information is on Brightspace. Okay, last lecture for this series. Today on ordinary differential equations, chapter 7 in the book. And so let's look at the content. Yeah, so what is an ordinary differential equation? And let me give you an example. What is that? Standard question. And as an example, I just write a ordinary differential equation. And because in that word we see a couple of things. We see ordinary, we see differential, and we see equation. So let me write an example. Y dot equals y squared minus cosine omega t. So first of all, why is it ordinary? And then you can say, oh, ordinary opposed to posh or elegant or upper class. No, there's nothing to do with that. Ordinary is because it's opposite the thing called a partial differential equation. So it's the opposite of partial differential equation. And what is a partial differential equation? Well, let me give you again an example. du dt equals du dx squared plus du dy, that should be u, sorry, plus a function of x and y. So what do we see? We see partial derivatives here. And so we see a derivative with respect to time and a derivative with respect to place, and it is a function of place and position. So, well, this can be a wave equation in elastica or something like that. Now, these are highly complex equations which we usually solve by discretizing into space. And if you then discretize this into space, then again you come up to this ordinary differential equation where you only have one variable at time. Of course, you can also do the other way around. You can then discretize with respect to time and then just solve for place. And those are two strategies in that case. But that's not what I'm going to talk about today. So talk really about this ordinary differential equation. So that's why it's ordinary, and why differential? Well, because we see a derivative in the equation, right? And for the rest, yeah, some from the depending on the function value itself and depending on time, the thing which you do your differentiation with respect to. Okay. So that is why we talk about ordinary differential equation. Now let's do a case study, and this is really a case study which is very applicable to mechanical engineers. So we're going to look at a forced, and maybe I should say a periodic force. A periodic forced mass spring damper system. Mass spring damper system. And then, well, what is it? Let me draw a picture. It's more than 1,000 words. So we have a mass somewhere here, which is just a block. It's just one-dimensional problem where we look at today. So there's only one displacement, x. It's periodically forced, so there is apparently a force here applied, and it has some amplitude p, and it has a cosine omega t. So that's the period by which I'm oscillating the thing. Then it has a spring and a damper. So apparently there is a thing which we usually draw like this with some spring stiffness K, and there's some dashpot damper which we usually draw like this with some C for the dashpot. And then the thing we want to know is, well, what is the position as a function of time? That's the thing we're interested in. And well, how do you solve that? The solution to that is, first of all, we need to write down our equation of motion. So we need the equations, our equation of motion. And how are we going to get the equation of motion? Well, we make a free body diagram, right? So we make a free body diagram. And in this case, it's just linear motion, so we only have to look into this direction. And maybe the thing is, essentially, it will probably be moving If it's not in space, it will be sliding over a table or something like that. But for now, we're not so interested in that. We're only interested in the linear motion. So the free body diagram, the FBD, for this case is now, so we cut the whole thing loose from our environment, and then by cutting it loose, we have to introduce forces. So this was the coordinate x, right? And then we have this applied, and this is the mass m. We have this applied force P cosine omega t. Then what else do we have? We have a spring force, which is pulling back from the spring, and we have a damper force, which is also resisting the motion. So those two forces resist the motion. Then we write down our sensitive today. So we write down Newton's law. Newton's law tells us that the sum of the forces equal the mass times the acceleration. Well, what is the sum of the forces? Well, if x is the positive direction, then we have a P cosine omega t minus the spring force minus the damper force equals the mass times the acceleration. So now we need some material behavior, some constitutive behavior, to say it in a very nice word, of the spring and the damper, and that is that the spring, well, let's take a linear elastic spring, minus k, go back. Spring force is k times x, and why is it not minus? Because I already defined the force in the other direction. Now, of course, that is a tricky thing, the signs, with the pluses and the minuses. And indeed, I do agree, that is one of the most difficult things in mechanics, to work with the pluses and the minuses. Okay, so Fs is k times x, and then for the damper we write that's a constant times the velocity. And then what do? Oh yeah, we plug everything into the equation here, and we get P cosine omega t minus k times x minus c times x dot equals mx double dot. Usually we rearrange that by putting all the things with the coordinates and the time derivatives on one side and all the other stuff on the right hand side. So then we write mx double dot plus c times x dot plus k times x equals p cosine omega t. Okay, so that is a nice example. Is this an ordinary differential equation? So that ordinary differential equation. Well, yeah, yes and no, I would say. And why would I say yes and no? Because I see double dots and a single dot here, and when we go back to the beginning, where should you begin? Well, you should always go back to the beginning. I only saw one derivative, a single derivative, a first order derivative. So how are we going about with such a second order derivative? Well, all the methods we will be talking about are all derived, well, most of them are all derived for first order systems. So this is a second order differential equation. And mostly all methods, mostly all numerical integration methods, because that's what we're going to talk about, are for first order systems. Okay, so then the question is, how do we transform our system into those first order systems? Well, that is easy actually. You just introduce a new variable. So you go from one second order equation, you go to 2 first order equations. And why? By introducing new variables. And as an example here, if we want to get rid of x dot, we have to write it as a single derivative. Well, very intuitive in this case. You say, oh, then if I define x dot as as being v, then x double dot is apparently equal to v dot. So now I have a single derivative here. So now with this, I can rewrite the first equation, and I can write m times v dot plus c times v plus k times x equals p cosine omega t. So now I have two equations, right? Because I don't want this. I have this as my equation, and the other equation is x dot equals v. So this is now my two sets of first order equations. Of course, I have to write them in a nice form, like x dot is v and v dot equals everything, push everything to the other side of the equation. So then I get minus k over m times x minus c over m times v plus p over m cosine omega t. Now everything is in a first order form, and we can now introduce a vector. For this case, we can write, we have a vector y, and the vector consists of variables x and v, and then we can write, y dot is a function of y and t, and that is exactly how it is written here. And then in a very general way, we now can use this as, first order derivative. It can be multi-variable, number of variables, function of the variables and of the time itself. Then for numerical integration, because that is the topic of today, for numerical integration, we can now, for instance, if it's a first order system, we can say, as an example, the new position, that is the old position. Maybe I should put time in there, right? Should say it with time. So at the time t plus delta t equals position at time t plus, well, a very intuitive way would be to say that is plus the velocity times the time increment. That's the way how you calculate how late, at what time will you be home. Then you think, it's like 15 kilometers, and I cycle about 20 kilometers per hour, so probably in 3/4 of an hour I will be there. So that is the arithmetic which goes on with, I'm here, I have this velocity, and in that amount of time I will be there. So that is this single step. And the same thing you can do, of course, with the velocity. The velocity is the velocity at time t plus the time derivative of that velocity times delta. Okay, and this is a nice way, maybe I should have written here x dot, and then you recognize, x dot v dot, those are exactly the quantities here. And this is a nice way for integrating, a very simplistic way. We call this the Euler step, numerical integration step by Euler. And if you can graph that, right? You can say, here's a function of time. Here we plot position and velocity. Say we start with our position here, and we have some finite velocity here. And then since we have a finite velocity and the position here is 0, then after a short while, this value times delta t will have increased. Now, so let's assume that the velocity is increasing, something like this. Then in the next step, we do again an increment. Well, it will be a little bit more steeper because the velocity is higher now. And then let's assume that the From that moment on, the velocity drops down suddenly, something like this. Oh, I should have used different colors. Well, anyway, I can do a trick. No, let's not do a trick. I'm not going to do a trick. So this is the velocity, right? So velocity. That's confusing. There's velocity, and this is position. Then and then of course you can stitch on and on and on forever. What was it? The velocity was lower, so we go something like this, and then maybe the velocity is constant. Then this goes like this. Well, anyway, you can think of any system, and then you step through it. And if you want to have more accurate result, you should make your your delta t smaller. No, you should make your step size smaller. So this is this step size delta t. Okay, let's go back to our problem. So this is a very which you can imagine. You can put it in a computer. You can do multi-step. There are a zillion of methods. We will talk about that in a second. So that is usually the scheme. Now let's go back to our problem. And remember, our problem was something like m x double dot plus what was it? C times x dot plus k times x equals p cosine omega t. Now, first of all, how many parameters has this problem? So the number of parameters, and by that I don't mean position or time. That is not the parameter, but I mean how many physical constants are there in play. Well, the parameters we have is, of course, we have mass here, we have the damping constant, we have a spring stiffness, we have an amplitude of a forcing, and we have a frequency omega. So in total, the total number is 5. We have 5 parameters. So if we want to analyze the system, that means that we need a 5-dimensional space. So I need to draw a thing with 5 axes, with these 5 fingers of my hand, and then this 5-dimensional space. For all these variables, I can draw solutions. To be frank, I have no clue how to draw in a 5-dimensional space. I can only do a number of projections then, and so that's complex. So, but there's a solution. We can apply scaling. So, if we apply scaling, well, how can we scale? We can scale with length, right? Length. So that's meters. We can scale with mass. That's also a physical constant here, kilogram, right? And we can scale with time. In our case, seconds. So we have 3 scaling variables, meaning that we can get rid of 3 physical constants if we scale everything with respect to some value. And I'm now going to do a very strange scaling. So for scaling, I choose the following. I say the mass m is 1 kilogram. Okay, so now I have a mass scaling. That's okay. But the next step is maybe a bit more tricky. For the stiffness k, I also scale 1 Newton per meter. Now that is strange, because a Newton per meter, that has a lot of physical constants. It's not meters, and it's not time. It's everything actually. It's Newton, which is kilogram meter per second squared per meter. Oh, the meter goes away, so it's kilogram per second squared. So this together with this does some time scaling, right? And then finally, I'm going to also scale with P. The forcing is 1 Newton. And this 1 Newton then is a kilogram meter second squared. Oh yeah, and then this guy and this guy, so the one of the forcing and the one of the stiffness, they do the scaling of the length. So it's a bit intertwined, the scaling here, but well, it's not so difficult. If you divide P by K, then you have a sort of a unit length thing, because that is a static elongation of the spring. and if you divide k by m, you get a time, and then you take the square root out of that, and you have like a frequency, or that is a time scaling. Well, it's all not so hard, but I'm not going to do that here. I'm just keeping it like this. And then with this scaling, and I can rewrite the equation, and then I write x double dot plus, I still have this c variable, right? And so, but it's now in a scaled version, c times x dot plus x equals cosine omega t. Because the omega is not scaled, I still have that one. And that's also a scaled variable. Well, for now, actually I want to write it like that. X double dot plus 2b x dot plus x equals cosine omega t. And there's a bit confusion now which omega, but for now I'll leave that be. Meaning now, with this scaled version, I only have two parameters. That is the relative damping, B, and the relative forcing frequency, omega, because that's dimensionless, it's divided by the time scale, and the time scale you get from dividing these and taking the square root. And it simplifies our problem a lot, because now we only have to play into a two-dimensional space to in a two-dimensional space. Why do I have two-dimensional space to analyze the thing? So I propose let's do that. Let's take this equation and let's program that thing in Matlab, and let's look at some time responses by doing numerical integration, because that is the topic of today. How do we do that in Matlab? Okay, so then I have to move to Matlab. Where are thou? Yeah. I already had opened Matlab. Yeah. So here we are. Here's my Matlab thing. It's not so interesting. Yeah, so something like this. Let's scroll this so that my equation is on top of this, right? Yeah, maybe before we start with this, we should rewrite this guy into this first order form, because that is the way we need it in our system, right? So again, with one of our variables are now, our vector of variables is the position x and the velocity v, and then y dot is of course this vector x dot v dot, and that equals, well, what does it equal? Well, x dot equals v, that is simple, and then the next equation v dot, then we have to look at this equation, is minus x, and then minus 2b v, right, and then plus cosine omega t. So, and this is now the system that we're gonna program in our Matlab script. So let's scroll that up a little bit so it's visible. Yep, and then we go back to our Matlab thing. So, well, we have to start a new script, right? Is it script? I don't know, new script. Yeah, something like this. And then what do? We write on top of it what it's about. So it's an periodic forced mass spring damper system, and it's scaled, and well, sometimes we even write an equation here, like do d2x d2 squared plus 2 times b times dx dt plus x equals cosine, like that. So then we know what we're talking about. Even could say that b is the relative damping, and oh, not relative, here we go, and then v or omega is the scaled forcing frequency. I'm a bad typer. Here it still is okay, but okay. Oh yeah, and we write by whom, man? By Matlab, and today is 10 December 2020. Okay, I cannot postpone the work anymore. This is really like work. You take a little bit of coffee and you snack something, you read some email, and now I really cannot postpone doing the work. So let's start with the parameter values. So we need parameter values. Let's say for relative damping we take 1 over a small value, and for the relative forcing frequency, and that means is it the frequency above or below the frequency of that forcing? Well, we can take it like 2, so it's above, it's twice as high as the natural frequency. Then of course we need some initial values, initial values of the thing. So in our case we have a 2-dimensional system, so y0 is a position and speed. Well, in our case it doesn't really matter because we just start from 0. Okay, now now we have to define what is our differential equation. So we write a function, and the output is dy dt, right? And how does the function go? Yeah, and what is it? Is the ordinary differential equation of a spring mass spring, what was it? A mass spring damper system, MSD. ODE MSD. Okay. You can even make it a bit longer. But mass spring damper is a lot. A single mass maybe. Well, whatever. Mass spring damper. The input is, now we have to follow the syntax of Matlab, and in this case it's time and then vector, and it's not the other way around. We will see in a second. Then we have to write our function. Well, I personally always like to unpack this state vector into sensible variables. Unpack y in named variables, so you can understand them. So I say x is y1, that was the position, and v is y2. And then now we can write our differential equation. So we can write dx dt. We cannot write that in Matlab, so we can write dx dt, right? And what is dx dt? Oh, that's v. That's simple. And dv dt is what was it? Minus x minus 2 times b times v plus cosine omega times t. And t is a variable, so that's there. Now you immediately see a problem here, that if I define my variables here, I don't know them here. So apparently I have to put my variables here, right? And not here. Okay. Then my parameter values. Then this should work. It will count. And now I have to put it back in this vector. So I have to create a vector, dy dt. Yeah, there are a zillion ways. It is a column vector, so it's zeros, and it has a 2 by 1, right? And then you can say dy dt. Wow, this is a bit. Why don't we do it like this? Why is dx dt dv dt? That also works. Yeah, almost. Okay. And then we say end. So this should give us back the derivative at time t at this state, as this position and velocity. Position and velocity gives back the velocity, and then and the acceleration. Well, looks jiffy and okay to me. So now we have to integrate that, and for that we have a number of functions within Matlab. And those are ODEs. So you could say help ODE 45 is a very famous one. Oh, I never used the help here, by the way. That was sort of stupid. Well, anyway. So ODE 45 solves a non-stiff differential equation, medium order method, blah blah blah. Actually, to be honest, if I look up stuff in Matlab, I almost never use Matlab itself. I almost always go to Google, and there I just type Matlab ODE. Oh, not ODE. And then I just I click on this, then I get a long story probably. Yeah, a long story, but I already know, yeah, I want to have ODE 45 because I read the long story. And then I go here. And yeah, this is also MathWorks, but for some reason I like this. And then because, yeah, you get nicely this statement, ODE function, we just made that function, right? T-span and then y0. Well, T-span is the start time and the end time, and y0 are the initial conditions, and then the output is the position and the function values at all these, the time and all the function values at these different positions after numerical integration. So this is the thing we're going to use. Copy. Here we go. Matlab, where are you? Here. Yeah. And then here, right? Okay. No chat. That's good. Yeah, time is also good. Okay, so then we paste that here. I tend to write this in capitals because that is the whole array. You could also say T array or Y array. Or the ODE function in our case is ODE mass spring damper, right? And the T-span, well, we have to create a T-span. So T-span equals T0 to T end. So now we have to come up with a well, T0 is of course is 0. And how long do we want to integrate? T end is I don't know, 10 seconds or 10 scaled seconds, right? I don't know, 10 scaled seconds. Yeah. And then y0 we already have. Yeah. And then we want to see some results, right? So say plot results. It's not results. Plot the results, and that is a figure. And we want to plot as a function of time this. Put the grid on, and the legend is the legend is label 1. Label 1 is x, that's a position, and label 2, and that's a speed. Yeah, and the x label is time, right? Time, scale time. Oh, it's not label. Label. Okay, well that should work. Fingers crossed. Circle of death. Oh yeah, we have to save this. Okay, this call it test 1. Oh, not enough input arguments. Y1. Not enough input arguments. What did I do wrong? Not enough input arguments. ODE, MSD. Is my function not working? What is going on? Okay, so if I do ODE mass spring damper and I say T0, Y0. Oh, I can, oh, spelling is horrible, huh? MSD. Yeah. What is going on, guys? Help? Iemand? Oh yeah, of course. I should have read the manual. I should have looked at the... Yeah, if you call that function, if you use that function, you have to say it's a function, right? You have to use this magical ape symbol. Why? Because it's not a variable, but it's a handle to the function. So instead of ODE, I have to write here @ sign, and then, because this is a function name, it's not a variable, and then we run that again. Okay, and then we get something somewhere. Where are we? Oh yeah, clear. Okay, we see some results here. So what do we see? That's a function of time, position and speed. In this case, position is, what is that, blue, starts at 0, velocity also. We see this type of figure, okay, and then this wobbly, okay, maybe it's correct, I don't know. I would expect that after a while the thing will be oscillating periodically, so maybe we should integrate a little bit longer. 50 or something like that. Yeah, and we see a nice periodic result, right? So and you can check, of course, when the velocity should be the derivative of x. So if the position is, if this is horizontal, then the speed should be 0, and of course that all complies. Of course, in the beginning it's a bit different, maybe, and that has to do with some transient behavior. Now we can play around with the parameters, but we have to do that here, or originally I don't like it to do it here. So, but there's a way. There's a very neat way to do that. So yes, you can have the parameters here in your main function, and then we put them into a structure, par.x and par.y. But now we have to give those parameters to this function here, so par, and then instead of b we write par.b here, and here par.w. Now how do these parameters from here come via this call into this? Then you have to pass them on to the ODE function, and if you read in the manual, you see that you can give options, and somewhere else you can also see that you can give parameters in the problem. So first of all, you have to give options. Now the options we use will be empty, so we have no options at the moment. We can read later on what the options are, and then here we put the parameters. Now it is not immediately clear from this part, but if you type, if you take the complete help of the ODE, it's somewhere mentioned about passing on these parameters. Summary of the ODE options. Oh yeah, these are the options which I had empty. Oh yeah, this is a nice one. As options you can also, for instance, do some tolerances. So about how accurate should my integration be. That is also a nice way. But for now I have no option, but I pass on these parameters. And since it's the last in the list, I have to put options, but in this case 0 options. Now so these numbers are now passed on via this to this, so I can change in the main program what these values are and then can run it. So initially we had this, right? Remember? This was a result. Now let's assume we change our this frequency. We go from above the eigenfrequency to below, so we go to 0.5. Of course, before you do that, you have to know, what do I expect then? Well, I still expect a result which is in the same frequency as the forcing frequency, but in the beginning there will be a bit different stuff going on. Yeah, and again you see this this relative motion. Of course, you can now change damping. Keep this 2, and if we increase the damping tenfold, again we will see that the amplitude is of course smaller in this case, right? And the more periodic case, and more the initial transient will die out quickly, and we get a nice periodic case. So you can play around with this, but what I actually wanted to do is, yeah, you can change of course accuracy and so on, but I want to have a simulation on the fly. So because if you now look at this example, what you see is you give some values and then you say integrate from here to eternity, and eternity is in this case 50 seconds, and while it is running you have no clue what is going on, and then finally when it's done it gives you the end result. Now yeah, how do you do that? You want, while this is running, every time there's a result, you want to see something. Well, there is a way to do that, and what you then can do, you can put an output function. So as an option, you then say, well, I have an output function, output func, that's how you have to spell it, and then you have to give the name of the function. Well, there is already a standard thing called phase plot, and we will look at that in a second. So now I give this option, and that means while the thing is running, it will make a phase plot. And how does phase plot work? So let's open phase plot. Well, this is the standard way in which these output functions work. Pay well attention. So first of all, the name is phase plot. The parameter list is like in the ODE, the time and then the function value, and then you have job and parameter, and that is exactly, so this is exactly this list, only there is a job in between. Why is there a job? Well, this phase plot, they foresee that at the first time you have to do something, and at the end maybe you also have to do something, and while it's running you have to do something else. So this job has a number of values. It has init, it has nothing, then it's just running, and there's also a thing called done. I'm not using it here because I have to do nothing when it's done, but you could also add a done here. You can read in the manual all about it. Anyway, let's focus on init and job. So if we initialize our phase plot, then we first have to make a plot, and we have to put a point on the plot, and we draw some axes and a grid. And then as a flag is 0, we give that flag back like everything was okay, that is flag is 0. Then when the job is running, then we want to update the position of that point. So we have a nice plot point in the phase space. Phase space is horizontal x, vertical horizontal position, vertical velocity. Of course we can already make a phase plot here, and then a phase plot would have been, if we plot here what do we plot? The position, which is y this, and then y2, yeah. So that is the second column is the velocities, and then grid on. This is already a phase plot. Let's run that. Something happening? Yes or no? What is happening? Oh yeah, output function. Sorry, I was a little bit too quick. Let's do it for now with what is it? Ops is empty. Yeah. So the output will come in a second. I will just first show the phase plot. So this is a phase plot, right? Horizontal position, and here we have then the orbit, the velocity on the vertical. We see position is 0. It has a finite velocity, and it will zero velocity, but it will accelerate, and then it will finally get into this cyclic motion. And if you, of course, if you add a lot of damping, then it will quickly get there. So if we increase this to 5, then what do we get? It will quickly settle on this one. And if we have almost no damping, so 0, 1, then you will see it will take a long time, of course, and it will jump between these two, and then finally will settle back into this. And why this 2, this ratio of this 2? Well, because the forcing frequency and the natural frequency are in a multiple of 2. Of course, if we can change that too, if we make 3 out of this, what do we see then? We see zit. Here's the other. Where's the other figure? Oh, that's lost. Oh, I didn't plot it. Well, anyway, let's go back to 2 and moderate damping. And then we want to do the phase plot, right? So let's get rid of this one. So now we know what a phase plot is. Output function is phase plot. Yeah. Did I do that well? Yeah, that's of course ODE set. That is the function we need to set these things. Yeah. So with ODE set we can set all the options, as you can see here. ODE set, RELTOL, UPSOL. And which options are there? Well, here, read all about it. Output function, output selection, refine, stats, non-negative, events. Events is a very nice one. Then you can find out when is something hit in the ground, then I have to stop. That's one of the homework assignments, by the way. Okay, where are we? Output function. So run. Then what do we see? Ah, that's nice. So we saw on the screen, this thing moving. Now, you see, of course, I'm now also streaming, so, and then we see the final plot. Therefore, the demonstration lacks a bit in time because of the live stream is running and OBS and the whole thing. But you saw this dot moving on the screen. Let's do it again, right? Yeah, in the phase plane you see, and of course you can also make a tail on it, etc., etc. Okay, all very nice, and read all about it, what you can do with all these output functions. Well, another output function I would like to show is you can imagine that you draw a block and that the block is just moving like the whole thing is really moving. And that would be nice if you could write that in an output function like I showed here with phase plot. But first of all, how do you draw a block on the computer and show it moving? By the way, there is one very interesting thing in this new item learned, persistent P. What does persistent P mean? Well, if we the first time enter, then we plot a point, and then every time, the next time we update the coordinates of that point by doing set. Now, of course, if we go out this function and go back, then the whole point P is lost. We don't know, and therefore we need a variable called persistent. So, a persistent value is a variable which keeps its value within this function. When you leave the function, the value is kept. When you come back, the value is still there. So first time we create a point, The handle of that point is still available. Second time when we come in, we can do set P, because P is still there from the previous one, and then we can update the data, and therefore you see the whole thing run. By the way, there was a pause here, and with the pause you can make it faster or slower, whatever. Okay, that is persistent. That's an important thing to note. Don't overuse it. What did I want to show? Oh yeah, I wanted to show the animation. So we want to see a block moving. How do we do that? Well, we then have to draw on the screen a block and then have the block moving. Now, I already, with respect to time, I prepared something and I'll talk you through it. Open up. Open up. Come on, man. Open. Yeah, I call it animate. It's not running while the thing is integrating, but it's a post-processing thing. Your homework is to make a on-the-fly thing of it. But anyway, so we're going to animate after everything is calculated to motion. So we look what is the maximum and the minimum position where the block is. Then we have a size of the block, and then we plot a line, and then the block is just this list. These are the corners of the block, minus A to plus A, and now we go up and then to the left and then back again. So this is really the X and Y coordinates of drawing a block. Then there's an item called a filled area. So H is the handle to a filled area, and I make it blue. Then what do? I set the X data, that is the horizontal data of this blue block, to the initial data plus what we calculate from our simulation, and by that I just move the block back and forth, right? Okay, so let's run that thing then. Ja, eens even kijken. Yeah, and then what do I do more on the thing? Oh, no, take this off. I also plot the timestamp on it because, well, that's a detail, but the calculation is now not equidistant in time, so that's a bit of a problem. Okay, let me change a little thing here. To get everything ready. Change one little thing here. Yeah. Okay. Yeah. Okay. Let's run this animate. So after we have done this calculation, we're not gonna do on the fly thing, so the opts are empty. Am I gonna plot the result? No, not. I'm gonna just animate the motion, animate, and just plot the result. I'll do that in a second block. This is the nice way to make blocks, as you may remember. Okay, let's run the thing. Okay, what do we see? We see the block moving, right? Nicely, like an oscillating thing, back and forth. Now you can imagine, of course, with this piece of code, that the next step is you say, oh, I'm going to make it like phase plot, that while the thing is integrating, I can show the block. And maybe you say, oh, maybe I add an arrow to it, and that's the force. And oh, maybe I draw the spring, and then it becomes longer and shorter. Well, actually, that is your homework assignment. I can go on for hours with this, and I'm not going to do that. It is nice, it is fun, and but I want to stop here because there are so many ways by which you can change. You can use different integration schemes, you can refine your solution, you can print it, you can read the manual. Then what I want to talk about very shortly is about chaos. use the last 5 minutes to talk about chaos. Okay, let's kill this for now. Yeah, and we clean this, that's always good. Clear the commands, then we go back to my air server. Yeah. So I want to talk about chaos for a second. And I want to draw your attention to a paper by Ed Lawrence with a Z, and it's a paper from 1963, and the title is Deterministic Non-Periodic Flow, and it's in the Journal of Atmospheric Sciences. It's number 20. It's page 130 until 141. So a relatively short paper. Now, what is the connection with chaos? Well, Ed Lawrence was a meteorologist. Too difficult. And he looked at the atmosphere, and he made a model of the atmosphere. And his model was like this. This is Earth. And then Earth is putting in heat. Right? And then in the sky, in the atmosphere, or how do you say it? Outside there. Sky, high in the sky. The thing cools off, of course. Okay, and then what do we have here? We have here a viscous fluid. Well, fluid, I mean, yeah, it's air, right? But it's viscous, and you have to heat it or exert forces on it to get it moving. And what do we get? We get a circulation here. So we get that air is coming up and going down. And why? Because there's a temperature difference here. There's a vertical, there's a gradient. Usually the gradient is sort of linear, but it's linear with a distortion. So it's sort of linear, but there's a distortion there in the temperature. What is this T? Okay, so this is a model of the atmosphere. And Ed Lawrence was interested in, what happens? How does this evolve with time? And it has to do, of course, with seasonal things. And so then he made a model of that, a very simplified model, and he came to these set of differential equations, ordinary differential equations. And finally, with 3 variables, of course, the model is more complex than that, but he broke it down into 3 variables. And note that I have a number of constants here. Rho minus 1. Now, what are the variables? Well, first of all, the first variable is the temperature distortion. Distortion in the vertical direction. Meaning we have this linear here, and there's a change in that linear, and this variable describes how distorted is it from linear. Because normally with conduction you have just a linear temperature drop. But in this case that is the constant thing, and this is the small variation on that. Then the second variable, that is the intensity of the convection, convection. And then the last one is the temperature difference between ascending and descending flow. So that there is between these, there's a temperature difference in one up and one going up and down. Okay, This is the differential equation, and although it looks linear, it's not linear. Note, because here is a y, so you have y times z here, and here you have y times x. So there is a nonlinear coupling. Note these terms, and these are constants. And what are the constants? Well, sigma is it all has to do with flow. But I'm not so good at the flow stuff. That's a Prandtl number. That's the dynamic viscosity divided by stiffness. No, I don't know. Rho is a Rayleigh number with the heat supplied and the loss. Well, yeah. Well, read all about it. Beta is the aspect ratio of the block. And meaning how thick is the atmosphere, on what scales are we looking. Now, Lorentz was looking at the following parameter case. Sigma is 10, beta was 8 over 3, and rho was 28. Anyway, then what did he do? Well, he analyzed this case by numerical integration. And then he found the following behavior as a function of time, and we will look at the paper in a second. He found the following behavior, like this, and then this, and then this for one variable, and then the other variable did this, like. And that is exactly what we're talking about now. It looks like some chaotic behavior. Well, why? Well, when he changed the initial conditions, then he got the following result. When he changed them a little bit, he got a result like this. And he got this. And that was only with a tiny. So this case was epsilon from this one. A very small change, and a very small change already gave a dramatic other result. So let's look at the paper. I have it somewhere, and I will put it on the web too. Where is it? Yeah. Okay, let's put that here. Yeah. Okay. No, I don't want to do this. Go away. This goes away. Okay. That's good. Okay, then we are here. So here's the paper. Let me check. How does it look for you? Looks good. So, deterministic non-periodic flow, right? The paper by Ed Lawrence from 63. Yeah. He goes into the whole motion of explaining what the problem is, how he comes to the model, because as I said, these variable x, y, and z are already a very abstraction. And here he does numerical integration of the non-conservative system. Well, why? Because that system is not it's not linear, and so here he shows a step, a numerical step, like the next one is the previous one plus something like delta t. Go away. This is the one we saw, the simple Euler step, and well, here second order method, well, whatever. Partial differential equation, as I started, but then he breaks that down by assuming already solutions with small perturbations on that to ordinary differential equation. And then finally we have here his ordinary differential equation. Then he analyzes that, and here you see the results of his numerical simulation. So this is the time step and these are the variables. Now the first thing you see is if he shows only 4 digits. What a bad student. Why only 4 digits? Well, in those days computers were costly and you had only limited memory size and limited computing power, so you didn't have 16 digits, you only had a few digits. And then he calculated these results and he saw this strange aperiodic motion. And then he thought initially, but that's because my computer is not accurate enough, or my time step is too large, and whatever he did, he kept this aperiodic behavior. And then the answer finally was that he stumbled upon a thing called chaos theory, which we now found all very modern and normal, but in those days was really new. You have a deterministic system and you get non-deterministic behavior, butterfly effect and so on. Now let's demonstrate this in Matlab, and there's a nice thing called my-Lorentz. And what did I do? I programmed the Lorentz equation, and then around the solution I perturbate with a very tiny number. So I changed the initial conditions with a very small random number. And then here you see tiny times random, so it's 3 plus 10 to the minus 3, so it's 1 in 3,000 or something like that. And it's really little, and you would expect, that doesn't give so much different result, but watch what happens. So let's run it. Yeah, so we get a solution here, right? And I have to make this a little bit smaller now. Yeah. So we have here nicely a solution with all the variables, with the distortion, the intensity, and the temperature difference up and down. And we see, growing, oscillating, and then it's non-periodic, and that's because of the non-linearities, of course, but we knew already that. But now watch what happens when we change with a tiny little number. The result is almost the same, again tiny little, but quickly you see, they veer off in all kind of directions, these solutions. They go all over the place finally. Now bringing this into this XY graph, and in the end it's just painted, the whole thing. So small changes in the beginning can have dramatic changes after a while, and therefore it's so hard to forecast the weather, right? Now there's also a nice GUI where you can see that result, and that's not the one I wanted to show. I wanted just to run the Lorentz GUI, and that is just taking the Lorentz problem with these values and then playing around and then looking in the phase space. And we're not looking, I'm not looking in the phase space, looking in the real three-dimensional space, and then tracking the solution as a function of time as a comet. So every point in space is a solution, and then we stitch all the solutions in time after one another, and then we get these lines. So that is what I'm going to demonstrate now. That's the last thing I'm going to talk about, Lorentz GUI. That's a thing which is in standard in Matlab, I think, even. And then here you can choose parameters or whatever, and then we start the thing. Well, we see some initial value, and then the solution circles around that initial value, and then it seems like it's some stable oscillation, but in a second, and that's something you also saw in the graphs, then suddenly the amplitude, it grows until a value, and then bang, it goes down again, and then some other value is increasing, and that is what's happening here. This is a 3D view of the whole thing. Click on the axis to rotate. No, I'm not going to do that now, because, and then you see it grows, and then whoopsie doopsie, it goes to another. Yeah, and that is actually comes back again to that one. Click on the axis to rotate the view, So here we see, oh yeah, it's a three-dimensional figure. Well, play around with it. It's nice. It creates nice figures. So there are apparently two fixed points here and here. Fixed points meaning if you put those state variables in that the derivative is 0, but these are not stable. Around these you get all kinds of solutions. And then with different values you can look at that. Okay, I talked already far too much, but read all about it, this Lorentz equation. It's actually super cool. This finishes the fifth and last lecture. I keep the OBS open and I start Zoom for the office hours. No, not office hours, questions and answers, right? Questions and answers, that's how it's called. Questions and answers. Okay, so you're all invited to come to the questions and answers. Yep. And the questions and answers, what is this? Maybe I should change my video here. Yeah. Yeah. No, that's actually okay. This is okay. Yeah, we keep it here. Yep, that's better.
Good evening, Professor.
Yeah, hi Sandeep. Hi.
I could not submit my fourth assignment. I could not solve it the first week. Do I still get to grade other students? Exercise? No. Then I have to continue with the fifth exercise.
No, just so if you haven't handed in a homework assignment, then you will also not get a grading job. But there's nothing lost. I mean, the lowest grade still will disappear, right? There's nothing lost. Just continue, hand in homework 5 on time, and do the final project.
Yes.
Yeah.
I will do it.
Yeah. Okay. Any other questions? Nobody. Michiel. Michael. Dat was Michael. Mm-hmm. Hey, Anand. Hi.
Morning.
Hi, welcome.
Yeah, sir. Actually, what happened was I couldn't upload my assignment 4
Okay.
on time. Like I tried to open my Brightspace on 340. Like it says, please log in after some time. After some time, I tried to open through my mobile and upload, but I couldn't do within the time. I sent you the mail, uh, but I panicked and I sent you the wrong file too, sir.
Okay.
Um, I couldn't not. I finished my 4th assignment, but I could not do it.
Yeah. Do you have a question or because this is a statement? Do you have a question for me
Oh,
or?
uh, uh, yes, sir. 1 minute. Like, is it possible to reconsider it?
Uh, well, if you didn't hand in the correct assignment or if you were late, then there's nothing I can do because at the moment when it's handed in at the moment of the deadline, it's all passed and all the work is distributed among the others. And what else can I do? I mean,
Yeah, like, mm, actually, the thing was like I don't know why the right page didn't open, but I don't know. But in my phone it was it open, but as soon as I got to upload, I couldn't do it.
yeah.
Also, like I sent a mail to you as soon as.
Yeah, but there's nothing lost. Your lowest grade will drop out in doing the average on the homework assignment. So if you just do a 5, do a good job on 5 and do the final project, and you still pass the course, there's no problem there.
Yeah, like, but sir, like last assignment also I couldn't do it. Maybe like last assignment I could not do it because I
Oh, then you're in trouble,
this
right?
assignment, yeah, this assignment like I was like I have to finish it somehow, and I was working for last 2 days fully, night
Okay,
and day.
okay.
But
Well, let's see how it goes. Just stay in the race. Do homework assignment 5, do the final project, and hopefully you will pass with a 6 out of 10 or something like that. Who knows,
uh, yeah,
right?
okay, but this thing is not possible to reconsider, or at least like half a grade or something. I mean, 50% of.
I'm not grading. Your peers are grading, and the thing when after the deadline, I can do nothing. The system is out of my hands, right?
Yeah,
It's
yeah,
out of your hands, but also out of my hands. That's how these systems work.
okay,
Yeah.
yeah, okay, sir.
Okay. Take care
Yeah,
then.
thank you.
Yeah. You're
Yeah,
welcome. Yeah. Okay.
I'll try my best in next assignment.
Yeah. Yeah, okay. Yeah.
Yeah,
Please do. Please do.
bye.
Yeah. Mm. Okay. Well, I have the feeling that there are no more questions. Then, well, it was my pleasure this course. I'm looking forward to the homework 5 and the final project things. And yeah, then I close by saying enjoy your Christmas break, stay safe, and I will see you all back in some other course, I guess in